So if you are new to the Ask Tom session, you can review all of our old videos at the link that I will provide in just a moment. And you can sign up to see any of our upcoming sessions at this link as well. We typically have a session every month at the last Tuesday of the month. So if this is a good time for you, you're welcome to join us. And without further ado, I'm going to stop sharing and David can take it away.
All right, thanks, Denise. And if you could, Denise, just confirm when you can see my screen, please.
Yep, you're good to go.
All right, so welcome everyone, and really excited to share this new capability with you about spatial algorithms and enhancements in Oracle machine learning, and I'll be diving right into the details. And I'm actually going to turn off my camera just because I'll be doing everything from a monitor over here and don't want to everyone to be seeing the side of my head for the next 45 minutes. So I'm just going to turn off the video and focus on the demo and the presentation. So I just want to begin with sort of the bottom line up front, so to speak, just so you have a good feel for what this is all about. And then I'll jump back in a moment to give you the whole sort of overview and context and everything else. So what we're talking about here is spatial capabilities in Oracle machine learning, and it's specifically Oracle machine learning for Python on autonomous database. And so what this looks like, I'm going to just quickly log in to my Oracle machine learning environment in OCI in my autonomous database. And what you're going to see now, one of the things that you're going to see that's new is the fact that amongst all the examples that come with Oracle machine learning for Python, you'll immediately see new things, because when you type spatial to search for spatial, there's a whole bunch of spatial examples. They cover much of, but not all of the core features. We're going to be adding more of these and putting these on GitHub and etc. So what this is really all about is within the Oracle machine learning for Python environment, you have this capability now to work with spatial data and apply spatial algorithms, and that's really what's new. So an example of that is the ability to detect hotspots and cold spots and outliers from geospatial data. And not to get into any of the details yet, I'm going to get into them in a moment when I do go through the presentation. But what this is about are notebooks, the ability to do things like this, the ability to, in Python, in Oracle machine learning, to be able to create data frames which reference spatial tables in the database. And then once you've done that, the ability to apply spatial algorithms, like, for example, the algorithms that detect hotspots and cold spots, which happens to be situations where there's unusually sort of elevated values that are relatively higher than surrounding values or lower than surrounding values, and detect those hotspots with spatial algorithms, and then be able to render results and be able to push that data back into autonomous database, and then move on from there with whatever the overall workflows are. So these sample notebooks are really sort of atomic examples of specific sorts of functionality. We're also working on hands-on workshops that are sort of end-to-end examples. But I just wanted to start with the fact that this is what I'm going to be talking about: spatial enhancements within Oracle machine learning for Python. So I'll come back to this in a bit, but now to sort of give you the whole story about what this is, where it lives, what it does, and everything in between. So this is all about the spatial features in Oracle machine learning for Python, and the new capability, the new offering is Spatial AI. So when you hear us at Oracle start to talk about now Spatial AI, what that is a set of capabilities within Oracle machine learning for Python, and it allows you to detect patterns and make predictions, all based on spatial algorithms. So a couple of the acronyms that people are probably already familiar with and I've thrown around already, but just in case you're not. The two main ones here to introduce are OML4Py, which is just the acronym for Oracle Machine Learning for Python. So Oracle Machine Learning in general is just the machine learning capability that allows you to apply machine learning workflows on your data in the database. There's Oracle Machine Learning for SQL, Oracle Machine Learning for R, Oracle Machine Learning for Python that just gives you different programmatic interfaces to machine learning workflows. This is all about Oracle Machine Learning for Python. The other acronym is ADBS, which is Autonomous Database Serverless. So I think folks are generally familiar with Oracle Autonomous Database, just the self-managing, self-tuning database that is Oracle's sort of flagship product. And Autonomous Database Serverless in particular is the fully managed version of Autonomous Database. So again, fully managed, fully automatically secured and patched and everything else. And so that's the context for today is Oracle Machine Learning, OML4Py on ADBS. So hopefully that sort of those terms will now have some familiarity. And the big top level view of all this is it's really about the ability now to take geospatial data and not just do the sorts of analyses we've been doing with Oracle Spatial for many decades, but now get into pattern detection and making predictions. So what people are familiar with Oracle Spatial, and again, for 30, 40 years now, is the ability to store discrete geospatial data, points, lines, polygons, and to be able to ask explicit questions about spatial relationships and spatial sort of computations and measurements and spatial processing that has to do with just the relationships between things spatially. And of course, we do more than points, lines, polygons. Folks understand we do 3D, point clouds, network data, and all kinds of other stuff. But the essence, the kernel of it is really points, lines, polygons, and within the database, being able to ask the kinds of explicit questions with SQL that you see on the right. And what this is all about now with Spatial AI and OML4Py is about, again, having that same data that we work with in Oracle Spatial, but now being able to ask a different category of questions. So not just explicit questions about explicit relationships and measurements and computations. It's more now about sort of the results of applying algorithms to find things like hotspots and cold spots and anomalies and outliers and make predictions and predict values based on, in part, location. And you see that the arrows on the right are pointing not directly to the database, but pointing up to that brain icon, which is Oracle Machine Learning. But that's connected to the database, and that's really what Oracle Machine Learning is all about, allowing you to apply these machine learning workflows to your database content. So just also a little bit of hopefully to set the stage and maybe get a little bit of jargon out of the way in case it comes up later. I just wanted to introduce what are sort of 4 of the most common scenarios that we address with spatial AI. And this is sort of in general, not Oracle Spatial AI, but sort of, spatial machine learning algorithms in general. Really the point of having these capabilities in OML4Py is so that when there are scenarios where there's data that exhibit the kinds of behavior that we are well suited to address, then we're a great fit. And that's not for there are plenty of scenarios, machine learning scenarios, that aren't necessarily geospatial in nature, but lots and lots and lots of them are, including many that people wouldn't necessarily think of as being geospatial at the outset. And so these 4 sort of broad categories that we are well positioned to address, and these aren't the only ones, but these are sort of the main ones. So the first one would be where there's something that you're trying to predict, some variable, and I'll say property values as an example. And you normally would be developing models to predict property value based on all kinds of what are referred to as features in the machine learning world, or attributes certain in the sort of the database world. So you'd be making predictions of property values based on the square footage, the number of bedrooms, bathrooms, is it an updated kitchen, how big's the backyard. But there's also a predictive value or a predictive influence associated. Commonly, there's a predictive influence of what are the values of the properties surrounding the property. So that's an actual spatial effect. And there's a predictive value there. It's not the only predictor, but it's a valuable predictor. And where we come in with spatial AI is the ability to sort of harness that, to incorporate that, to not leave that on the sidelines, but to actually have that aspect of the predictive influence of surrounding, in this case, properties, have that be part of the model itself. And you can see other examples that I have listed there of other spatial effects. So the spatial effect would represent sort of a characteristic of the data, something that the data exhibits. And the jargon over on the right is sort of what it's referred to technically by sort of practitioners and what the documentation may refer to here and there. So what we're really about is identifying these and other sorts of spatial effects inherent in a scenario and being able to apply the algorithms that will incorporate and address those effects. And at the end of the day, it's like there has to be a like so what sort of a thing. Answer the so what question. And the so what question, the why bother, point is that you have a result which is a just a more reliable model, a model that will return better, more reliable predictions. And this is something that can be quantified, and you go to this extra effort and you end up testing and validating the model and determining whether these spatial algorithms and features give you a better result. And that's what it's all about, because if they don't, there's no point, but they do. And that's why this is really powerful. So with that very, very general context in mind, I want to just describe where does this capability live? And I opened up a notebook, when I started out, just to sort of show you what this looks like as a as a user. But architecturally, sort of where this lives in the stack is that this is a feature built into OML4Py on ADBS. I've introduced those terms. Hopefully, OML4Py and ADBS make sense. But this is capabilities built into OML4Py on ADBS, which means that it's not a separate download and install or configure or license or anything. It's just part. You spin up Autonomous Database Serverless. Autonomous Database Serverless has OML4Py. OML4Py has these spatial features built in, and so that's sort of the beauty of it. It's just there, and as such, it provides just the mainstream experience that OML4Py developers already work with, but now sort of extends that to provide all of these sort of spatial features, I'll say, in general. And a couple of the main aspects of that developer experience and what OML4Py is all about is, well, I showed you a notebook, the ability to have projects in OML where you organize your work into different projects. You have notebooks in different projects, and it's a really sort of nicely organized, efficient way to have your machine learning workflows set up. Proxy data frames are a huge one, and I showed that at the beginning in the notebook, or at least I mentioned it, where data frames are the way that Python people work with data, just like tables and views are the way that us database people work with data. Well, a data frame is sort of the essential data construct in Python. And really what OML4Py is sort of about having a place where a Python developer, a Python person whose comfort zone and expertise is working in the Python sort of environment, but letting them transparently operate against data in the database so that you don't have to like lift and shift and bring all the data into Python, do things with Python and push it back. Instead, you have what are referred to as proxy data frames, where you work with data in a data frame, the way that a Python developer works, but that data frame is really just a proxy, a reference to a table behind the scenes in the database. And that ends up being a great thing because you reduce like a ton of data movement between the database and the Python engine. And there's a bunch of other sorts of important aspects about OML4Py in general and the advantages and why it's so valuable to sort of bring the Python and database worlds together. And they're listed there because we're sort of, as part of OML4Py, we're part of all of that. We have the same behavior. Just to give a little bit more fine point on the key features of OML4Py Spatial AI. The first one in the top left is something that kicks in and is of value before you even get to the algorithms that do pattern detection and prediction and so forth. And that's the fact that Spatial AI provides essentially a Python API for several of the most common, like, valuable spatial operations in the database. So like within distance and nearest neighbor and any interact, those types of things that you do all the time with Oracle Spatial with SQL to search for things spatially and filter things spatially based on proximity. Well, it's obviously very important to be able to do that kind of stuff within a machine learning exercise. But again, the point of OML4Py is to be in the comfort zone of Python developers. So that data frame that I described, which is just a reference to spatial tables, it has methods to do these things. And those methods are really just, when the data is an autonomous database, these Python methods really just invoke the spatial SQL behind the scenes. So that's one important aspect. Pre and post processing, again, not even getting into the algorithms yet, but the pre and post processing is another important capability. So traditional important pre-processing like feature engineering, where you're using data and some computation to generate new features in the data. Well, with spatial, that's important because you may want to sort of enhance your data with a new feature that is maybe the number of items within a certain distance or the distance to the nearest something or other, because that may be predictive. So the ability to do that, the ability to fill gaps in data based on spatial algorithms. And then that third bullet, spatial weights and spatial lag, is a really important spatial pre-processing and step that'll come up later in what we're talking about. And just conceptually, what that means, sort of the jargon aside, is that many, not most, of the algorithms that we end up working with have to do with the relationship between, like, some observation, some value at a location, and the relationship between that and what's going on around it, and whether what's going on around it can help predict values or not. And so it has to do with neighborhoods, what's in the neighborhood of an observation. That spatial weights and spatial lag thing there, jargon aside, that is really what defines what do we mean for a data set, what do we mean by a neighborhood, and what is that relationship between an observation and what's around it. So that is like a real cornerstone of a lot of the algorithm work that happens, and that's part of what we have in our sort of pre and post processing. Then on the right is really the real machine learning aspect in terms of algorithms, and the five main categories I'll call out are regression and classification. So sort of classic prediction scenarios where you're predicting a numeric value or you're predicting a categorical value. Clustering, anomaly detection, and co-location. I think clustering is fairly intuitive. Anomaly detection maybe also. We'll look at a little bit more of that in a moment. And co-location, which has to do with the degree to which features or observations tend to align between two different data sets. And there's lots of situations where that's really valuable to know, where the degree to which things align with each other. And then the last one on the bottom right, spatial ML pipeline, is very much there as sort of an item for machine learning practitioners who work all the time with scikit-learn, which is a sort of a leading, if not like, leading machine learning package. And scikit-learn has a construct, or an operation of pipelining or chaining things together. Several algorithms, estimators that do some work and pass the result on to the next step and that passes the result on to the next step to go through a pipeline. And that's a real kind of foundational aspect to the way people, lots and lots of people that work with scikit-learn operate with machine learning. And we've taken that scikit-learn pipeline and enhanced it to know how to work with our spatial estimators, our spatial algorithms, basically. So people that are, okay, we want this to be in the wheelhouse, in the comfort zone of machine learning practitioners, and lots of them are very comfortable with working with pipelines. I am not going to drag through each of these and explain them. This is literally a screenshot. This is like grabbed out of the documentation, but I wanted to at least list for folks for whom this is, already sort of familiar with this, just list the algorithms that are in our first release. And this is all I should mention. This is really the first release of OML4Py Spatial AI. So this is the first set of algorithms that we've introduced, organized by these categories that I just mentioned. And we will share, if maybe Denise already has shared, links to the documentation and API, and that's where this has come from. And so I'm not going to get into these right now, but it may be interesting for some folks to see exactly what's in there. I should also mention right now, probably should have at the outset, that when it comes to spatial AI in general, there are sort of two very broad categories, and we're completely drilling down with this whole presentation and what we've released in our first version. We're drilling down into one of those two broad categories, which is, we'll say, discrete point line polygon data, something that we've historically referred to as spatial vector data. However, now with the emergence of vector DB and AI, it's not a great idea to talk about vectors, because people think about something else now when we talk about vectors. But this is all about what we've historically called spatial vector data: point line, polygon data, discrete data defined by coordinates. Well, the other side of the coin, of course, is raster data, imagery, remote sensing data. And there's a whole nother world, a very wide and deep world of spatial AI that relates to raster data, things like object detection and so forth. That's obviously something I'm not talking about in this session, but that is something that is in the works. And the other side of the coin, that raster side, is something that you're going to see happen. So stay tuned for that. But for now, we're just sticking with the this discrete geospatial vector data side of things. So one other sort of slight drill down for those that are sort of interested in a little bit more of the detail. So I mentioned how one of the real key benefits and capabilities of OML4Py is this notion of a data frame that's a proxy to data in the database. That's sort of a foundational aspect of OML4Py, and a beautiful thing, because it means you're not always moving lots of data between the database and the Python engine, because you don't have to. In the world of spatial AI, we do that, but because of the nature of spatial data and some of the requirements around how that data would be sort of provided and handled in the way that we work with spatial data, we have what's depicted here on the right in terms of our spatial data frame. It's a proxy. You can see on the top left in red, spatial data frame. There is a spatial data frame, this one sort of object spatial data frame, and it's a proxy to some data somewhere. And of course, it can be a proxy to data in ADBS, a spatial table, and that's the one on the left. But it can also be a proxy to data in other locations, like, for example, object storage. You could have GeoJSON files and shape files sitting in object storage and create a spatial data frame that's a proxy to that. And similarly, you could have data in something called a geodata frame, which is one of the most common way to store geospatial data in sort of a spatially enabled data frame in Python. It's the way tons and tons of people, spatial data science people, work with spatial data. We want to make sure that our libraries, our algorithms, will work with data in these various locations, because there are times when it makes sense to do that. However, our real course, our focus, and where the real power lies, and where I'm going to say 90-odd% of, where, how this will be used is when there's data in ADBS. When data is, loaded into ADBS, and one of the reasons that we provide these different proxy options is that you may start with a bunch of shape files in object storage or GeoJSON files in some attached volume that you've loaded. Well, we can create a spatial data frame that proxies to it, and then we can write that spatial data frame to a table in Autonomous Database. So this whole environment allows us a lot of flexibility in terms of where data originates, where data ends up residing, what you're proxying to. Maybe you're going to sort of combine some data from the database and some data in object storage and work on them collectively. There's a ton of flexibility here. But what I want to really call out is a very important aspect of this for Oracle Spatial users is the fact that when a spatial data frame is a proxy to data in the database in ADBS, which again is going to be the bulk. I mean, that's really how this is going to be used by and large. So when it's that blue connecting line on the left, then when you perform one of those spatial methods on a spatial data frame, like a within distance or a SDO or a point and polygon sort of operation, what happens is the following. A Python person will have a spatial data frame, maybe called spatial data frame 1, that's the name of my spatial data frame, and apply a method. For example, I want to know which items in my spatial data frame are within some distance of an item in another spatial data frame. That will be done using a very familiar Python sort of syntax, but behind the scenes, because it's a proxy to Oracle Spatial, it transparently turns into what you see on the bottom left, which is just familiar to anyone using Oracle Spatial, in this case, a within distance query. And that's part of the beauty of this, is that you're actually leveraging the horsepower of Oracle Spatial while working entirely in a sort of a Python data frame sort of environment within Oracle machine learning. Okay, so I want to show a few examples, and these are just sort of some screenshots to show what some very basic examples look like. And the context here is, I think pretty much all of these involve working with some US Census data for Los Angeles. And the US Census Bureau, well, obviously they collect information about people, places, and things, and demographics, and they aggregate and summarize the data about people, places, and things, and counting people, and developing statistics about all sorts of demographics, and they summarize that by different geographical units or different sort of hierarchies. Obviously, to sort of have things be anonymized, and also to be able to understand broad trends and characteristics. And I think the second to the lowest, most detailed geographic unit in this hierarchy of geography of the census are something called block groups. And that's what these individual little shapes are. And I just happen to be color coding them in this map based on the median income of all the residents of each of those block groups, which is an example of one of the demographic values that the Census Bureau collects. So these examples are just using this data to show a few of the things that I've described. So the first one is so now we're just showing some screenshots back in the same notebooks that I showed you when I started out. We're in Oracle Machine Learning. How do I want to get started? Well, in this case, I've already have a table in the database, a spatial table. It's called LA block groups, which are the census block groups for the city of Los Angeles. Well, the very first thing I might want to do, if I'm going to do some pattern detection or prediction, I want to have a spatial data frame to work with, which is just a reference to or a proxy to that table. And this is what it looks like. And you can see surrounded in red there is how I create one of these things, spatial data frame.create. And it's a DB, a database spatial data set, and I specify the table. If this had been a data set that's in object storage, it wouldn't be a DB spatial data set. I'd be supplying some information about the storage bucket. But in this case, I'm pointing to a table. And so what I get back, and the line 1 there is to create the spatial data frame. Line 2 is just to sort of print it out. And as you can see here, I now just have a reference to, I have a spatial data frame in OML4Py, which is simply a reference pointing to a table in the database. Now, the next thing I might want to do is maybe perform one of those spatial operations. Maybe something I'm going to want to do is I'm going to want to engineer a new feature, which is counting things within distance of other things, for example. So in this case, I want to use one of those methods. So I've got a spatial data frame, if you see surrounded in red, called schools. I've gotten to use that underscore SDF suffix to indicate spatial data frame, and sort of got comfortable doing that. So I'm saying schools, spatial data frame, pointing at a table of schools. And I'm going to do a within distance operation on that. And what I want to know is which schools are within, in this case, 2 kilometers of a specific census block group. So it's a method, a within distance method on my school's data frame. And then the within distance wants to know within distance of what. And then inside there, I'm specifying from my block group spatial data frame a particular GeoID, the ID of that spatial data frame, and the distance, 2 kilometers. So doing that for a Python person, great, no problem. And then because all of this data, the schools, the block groups, because it's all just tables in the database, when I click run on this paragraph, that's being shipped to the database as an SDO within distance query. And of course, there's spatial index, and it's gonna, even if there's lots and lots of data, it's gonna work nicely. I didn't have to load things into the Python engine's memory space to perform this and do it all with like sort of logic in Python. This is really just telling the database to do a spatial query. And that same sort of thing, sort of having the database run a query from Python becomes interesting again when you're using this for something like spatial, feature engineering. And here's an example of that. So in this case, I have an existing set of these block groups. That's just a table in the database, this block groups table. And I want to add a new feature to it that I might want to use for some prediction. And I want to know for each of those block groups, what's the distance, how far away is the nearest school from the boundary of that block group. There may be a school in that block group, in which the case the distance would be 0, but most of these block groups are really small. Most of them there will not be. So I want to add a new feature to this data, which is this new numeric value, which is how far is the closest school to each of these block groups. So you can see in the top surrounded in red is I'm going to create a brand new spatial data frame, which is the result of running a nearest neighbor. That's all I want to do for each, So, and I'm not going to get into the details of the syntax here, but the upshot of it is this is just another case of using Python to structure a spatial operation. All the data is in the database, so this becomes an SDO NN, like a nearest neighbor query in the database. And then I'm just displaying the result, including that new feature that I might want to use for training a model to predict something, because maybe there's some predictive value in that distance to the home values or something like that. That's one example of pre-processing, right? Engineering a new feature. Another example of pre-processing is filling gaps in data. And that's a process referred to as imputation. And the algorithm that fills gaps is an imputer. So imputation is done by an imputer. And generally speaking, when you have missing values in data, you'll tend to fill those missing values with some aggregate of the rest of the non-null values. Maybe you'd pick like the median or the mean or some other statistical aggregate of the values that are not null. And many times that's perfectly fine. I talked about scenarios where our features kick in, and this is one of those scenarios. So one of the things that we can do is fill gaps in data, not just based on a summary of all the non-null values, but instead with a summary of the values within its neighborhood. And you can do that, but what's your justification for doing that? Because if there's no real relationship between the value at one location and the values of its neighbors, if there's no relationship there, then there's really no justification in saying I'm going to fill missing values with a summary of the neighbors. However, if there is a relationship, a correlation of values at a location and its neighbors, then it makes a lot of sense to do this. So what I'm skipping when I show you this is the fact that by applying this spatial imputer that fills missing values with the summary of their neighbors, there's tests that we do beforehand that are also part of this pre-processing that will establish the fact that there is such a behavior in the data that justifies doing this. So this is sort of an example of some of that pre-processing. You can see the missing values in red on the right, and after running the spatial imputer, the gaps are filled, or the gaps in red on the left, and after running the imputer, the gaps are filled on the right. So now getting into some of the actual algorithms that we apply. Well, the first, probably most intuitive one would be detecting density clusters, which just means you have some thresholds that you define that say when a bunch of observations are all all within a certain distance of another observation, and there's at least some certain minimum number of observations in this concentration, then we're going to call that a cluster, and we'll label all the observations that are part of that concentration with a distinct label. And what you can see here is us doing that. In this case, this is a different set of data. Now these are traffic crashes, and they're really just crashes all across this area, but I'm only displaying the crashes that are part of a density cluster, and each of them are color-coded according to that cluster label. So crashes that have the same color are part of the same cluster. So we do this in Spatial AI. You could then take the result, you could label the crashes, and it's back in the database where now you've sort of enhanced your crash data with a label that says if it's part of a cluster or not. You could then do operations in Spatial to like surround them with a rubber band to show the areas of clusters and all that sort of stuff. But this would be the first example of a basic algorithm in play. I mentioned before that there's operations that we do that are based on the assumption that there's a relationship between a value at one place and what's going on at the values of its neighbors, and how there's tests to determine whether that's actually true in a data set. And this is just a little screenshot of that test and what it looks like to evaluate that relationship. Without getting into the details of the numbers or anything, this is just an example where we are verifying the fact that there is a positive correlation of income, median income of a block group, census block group, with the median income of its neighbors. So there is such a relationship, and we would be justified in doing something like that spatial imputer. And once we do that, we can also do things like find hot spots and cold spots where the values that we see collected together in an area are collectively higher or lower than the surrounding values. And that's really what's meant by a hotspot. So it's different than a density cluster, which is just a tight concentration of observations. In this case, it's that there's observations everywhere, but the observations in certain areas are relatively higher or relatively lower, significantly higher or lower than the values of their neighbors. I'm not going to spend any time on this pipeline stuff. I sort of mentioned it, but for people that are used to working with scikit-learn, they'll be, I think, pleased to see that they can do what they're used to doing in terms of having a pipeline of operations that include something like a spatial regression model for predictions. When it comes to predictions, making predictions, we have a number of different algorithms that sort of are in a couple of different categories, and the suitability of an algorithm, using one algorithm over another, depends on some of the characteristics of the data or what sort of patterns the data exhibits. And based on the patterns that are inherent in the data, then there'll be an algorithm that will make more sense to use, that's more designed more to work with data that has a certain, remember I talked about spatial effects and different characteristics that we address. Well, one of the interesting things that we have is, in addition to these different algorithms and sort of the guidelines of when to use them, is that we have one of these algorithms is this thing in the red box at the top called the spatial adaptive regressor. And that's actually a regressor, an algorithm that will first take the data and sort of profile it and generate some spatial statistics that will describe what types of patterns exist or don't exist in the data. And based on that, this adaptive regressor will choose an algorithm. And based on, and in this case, you can see that algorithm chosen says lag model. That's just one of the regression algorithms. It's choosing that model because it's generated some spatial statistics that would indicate, based on the statistics, that would indicate that that's the best model. We actually also describe how you can generate those statistics and what the sort of the decision tree is, what the logic is to determine what the most suitable algorithm would be to use. So what's done here is actually something you can do yourself as well. I'll also mention that this adaptive regressor, it's a really useful thing, and it's something that we're working on and evolving and enhancing. So currently, it really only chooses between a few, like a limited set of scenarios, but we're making this thing smarter and smarter so that, the idea would be for people that are really familiar with this whole topic of, spatial ML algorithms, they might not want to use this because they have their own sort of best practices about which algorithms they prefer to use in different scenarios. But for someone that really just wants to make reliable predictions, this model, this adaptive regressor will actually go so far as to say, the data's been profiled and we don't see any spatial effect that any of our algorithms are going to really help with. So we recommend using a non-spatial algorithm. And so it's a very even-handed approach in that sense. But when there is a spatial effect, it will choose a spatial algorithm to use. So I'm going to jump back to the live stuff. But before I do that, I just wanted to make sure that these takeaways were hopefully transmitted to everyone. So again, this is all stuff that's part of OML4Py on ADBS and only ADBS. This is not something that you can download and install in your own database. It's not on ADB, dedicated. It's not on any other database cloud service. It is on ADBS and only on ADBS. It's made up of a set of algorithms and associated APIs for the pre and post processing and the predictions and pattern detection that I described. And like I said at the beginning, it also allows you to just run some basic spatial operations from Python that are seamlessly transposed to spatial SQL behind the scenes. These are a couple of links that Denise put in to the chat, so you can see the doc and the API reference. There are going to be hands-on workshops and so forth that we're working on, but at this point, you can at least get to this. And then the other thing, of course, you can do is exactly what I'm doing here, where you can, of course, just come into your own ADB environment and go to your, create an Oracle machine learning user and go into OML, and you will have exactly what I'm showing you here available to you. So you'll be starting from scratch, but you automatically have these examples. So again, if we go back to these examples, and anyone that's, of course, for folks that have already used Oracle machine learning, OML4Py, this is already an environment you're familiar with. You're just going to sort of have this gentle, nudge out to starting to take advantage of all this spatial stuff. If you're new to OML4Py, sort of familiar with Python, but new to OML4Py, then coming in here, there's all kinds of stuff to get started with OML4Py in general, which would really be a great place to start. So you can see all these OML4Py sort of basic notebooks on how to do just basic stuff. Has nothing to do with spatial or anything. It's good to sort of get yourself oriented with OML4Py. But the spatial stuff, if you just, again, search for spatial, you'll see now this whole pile of notebooks that involve all kinds of things, different aspects of pre-processing and feature engineering and cluster detection and regression, different spatial regressions. The one notebook and only notebook that you need to run in order is the first one, which is OML4Py Spatial AI Run Me First. That notebook seeds the data. It reads files out of object storage and loads them into tables in your schema. And those tables are what's used for all the rest of the notebooks. The other OML4Py notebooks, not the spatial ones, but all the other ones do the same thing. There's an OML4Py Run Me First. Of course, that doesn't have the spatial data. We have the Spatial AI Run Me First. That seeds all the spatial data. But after that, you can really kind of look, sort of browse the catalog of samples and run them in whatever order makes sense to you. You can also look at the documentation and then see, read about how something works, come over here and try it. So just to show you one example and step through it is, I think the one that I'm going to do is one on detecting outliers. And there's an algorithm called LOF, which stands for local outlier factor. That's not something that we, these aren't things that we invented. I, probably also could have mentioned that most of the stuff that we have in OML4Py Spatial AI is taking the sort of the standard state of the practice of spatial ML, spatial AI, again, at this point on this discrete spatial vector data, and enabling all that stuff in the OML4Py environment. So for example, people that work with spatial ML workflows, in general, local outlier factor is sort of a familiar concept. You'll see that in different libraries. Well, the point here is not that we invented outlier detection, it's that we've applied the standard sort of state of the practice way to do that and done it within the OML4Py environment. So let's just see what one of these looks like. Now, of course, I could click on this notebook and open it just by clicking on the link. But what you can do, and what I suggest you do, is instead, if you select a tile here by just clicking on it, and I've already filtered on this one notebook, but it's the same thing if you hadn't filtered on anything. Any of these notebooks, if you click on a tile, you'll highlight it. I just want to actually do this local outlier factor. So if you highlight it, you can make a copy of the notebook, which you can then edit, play around with, destroy it, delete it, make a new copy, because if I just click on it and open it, it's a read-only version. So I'm going to create my own version and I'll just call it something different. I'll say LOF, local outlier factor accidents. And then in OML4Py, in OML in general, you have projects where you organize your work. So I've just got one called Sandbox, just a playground. So I'm going to copy it into there. So I've got like a working copy. I could go to that project or I could just click open notebook. I'll actually go to it so you can see instead of clicking open notebook. So now projects, notebooks, and I'm in the Sandbox project here. I'm already in it. And there's the thing that I just created by making a copy. So I'm going to open that notebook now. And when you do this, the first time that when you open a notebook and run it, you're going to see it's going to say setting up running environment. It's spinning up a container, basically like a little containerized environment, a little runtime, a Python runtime, just for this notebook session right now. So that's how long it took. So now I've got a Python environment, and now I could just start stepping through this notebook and run paragraphs. So I can run paragraphs. It'll sort of describe to me what's going on. What we want to do is identify outliers in a set of crash data for the city of Chicago. Something else to mention is that there's a play button at the very top that runs the whole notebook. It just runs all the paragraphs one after the other, which you could do if you don't want to click, 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 click. But if you prefer just to run the whole thing, you can do that. So here's what I talked about before in terms of having a data frame that just points to a table in spatial. So I want to create a new variable in Python. It's going to be a spatial data frame. I'm going to create it. It's going to be based on a DB spatial data set. In other words, a table. Let me just make this bigger. So I'm creating a spatial data frame based on a table in the database and then just showing the first few rows of it. So here's our table of crash data. So as we go through this notebook, you know, I want to sort of get a little bit of a profile of the data. So I'm going to look and see what I want to do is only find outliers of like really serious crashes. So I'm just showing in this notebook how we can look at different injury rating and crash type. I just want to know what does an injury rating mean in terms of crash type. So this is just a little bit of data profiling, nothing spatial about this. This is sort of telling me when I look at it that what I'd like to do is just look for outliers of crashes where the injury rating was at least three or four, the important ones. So just sort of breezing through this, because you could go through all this stuff at your own pace. The idea here is that that what we're going to do is we're going to train a model to detect outliers. So in general, what you do is you take your data, you're going to sort of you generally would split it into training data and test data. We'll evaluate how well the model works. When it comes to pattern detection like this, when it's, you know, there's supervised and unsupervised learning. So if we're making predictions, we're trying to predict a value like home value, we would separate the data into training data and test data and see how well the predictions are met. This is unsupervised learning, just detecting a pattern like an outlier. So we're really just going to apply the algorithm and see the result, and then we could play with the thresholds if we're not happy with what it calls an outlier. So one of the things I mentioned also is this thing about how important it is to deal with what's going on in the neighborhood of a value. That was important when we're making predictions, like do the property values of neighbors affect our property value? Well, it's also in a totally different way. The idea of a neighborhood is important here too. We're looking for outliers. And so what we want to do is we want to look for crashes that are sort of an anomaly in terms of not having as many neighbors as other crashes. That would sort of be an outlier. So once again, the idea of a neighborhood is important. And this is just, you know, where we define this thing called spatial weights is what it is that defines what a neighborhood is. And in this case, you know, I've defined a neighborhood as being the 20 closest. The neighbors of a crash are the 20 closest crashes to it. So to create this particular model, we have this this algorithm, local outlier factor in Spatial AI. So I'm going to create a model based on that local outlier factor, and I'm going to train the model, fit the model to the data. I'm then going to look at it, and what that model does when I fit the data is it's going to put a label on every crash with this outlier factor. And this outlier factor is just a number that indicates how strongly this particular item is an outlier. The higher the value, the more of an outlier it is. The lower the value, the less of an outlier it is. And when you look here and you see we have these values 0.5, 1, 1.5, we have lots and lots of them down at the left-hand side. Those are all ones that really aren't outliers. But when we look at the outlier factors that are out on the edge, where there's only a small number of them, those are the ones that have a high outlier factor. Those are the ones that are outliers. So what we're going to see is that where the outlier factor is greater than or equal to, and I think that minus is a rogue minus, we're going to call that an outlier. So now I can just basically look at the results. So I'm going to plot the results here. And here I'm looking at what I've done is I've said that for every crash, I'm going to label the crash as being either normal, not an outlier, or as an outlier based on that factor. And I can see that in red, the ones in red are the ones that the model has deemed to be an outlier. Look, you know, and they generally look reasonable. Again, it's all based on what I've defined as being a neighborhood and the thresholds that I've set, and those dials can be turned until it's showing what you would want to be an outlier. Now, this is just taking an existing data set and applying this algorithm. The other thing that is really interesting is when we apply what are referred to as novelty outlier detections, which says we're going to train a model like we've just done, And then we're just going to start to add new data. And as new data come in, I want to say, is this data point an outlier? Is that data point an outlier? As new data comes in. So that's more like we've trained a model. Now we're going to have new crashes coming in, and I want to know whether they're an outlier. So now I'm going to do the same thing, but I'm going to say that this is novelty, meaning there's new data that I expect that I want to train. And what I'm going to do is create a bunch of random data points within that area. And so as those new data points come in, I'm going to say, if a new data point comes in, is it normal, or is that new data point a novelty outlier? So I'm going to do a prediction for that new sort of random data as it's coming in. I'm going to label the results for each new data point to say, is it a outlier or not? And then we will, we'll look at the results. However, I didn't do. So I'm going to run the whole notebook right now, and I've got 3 minutes, and that should be enough. So I hadn't run the last paragraph that shows that result. So I'm running the whole thing right now, and that should, so now, as you can see, it's going to go through, it's going to create training data, fit the model. This is what I showed previously. It's done this, local out. Okay, now it's training the novelty outlier for new data. I've created a bunch of random, this is sort of simulating new data coming in sort of randomly, labeling those random points, and then plotting a map. So here now in gray are all the training data. That's the data that we looked at the first time, where I had labeled which ones were outliers. But now all the red and green are brand new random points that I added. And as they were added, they were labeled as being novelty outliers, meaning they're deemed to be a new data that's an outlier, or if they're green, ones that are not outliers. And you can see of that new data what it predicted to be an outlier versus not an outlier. And again, I think the result made sense to me. Yeah, I could play with some of the parameters to make it a little better, but that's all sort of an example of one sample notebook. So kind of what you just saw. If we go into templates, this is the other way to get to the same set of examples that you get to by clicking examples from the homepage. But that was one sample notebook amongst all these spatial samples. So lots to play with. And again, the so what in all this is the value. Being able to, number one, when it comes to these pattern detections, being able to do that sort of stuff without having to take all your data out of the database. You're just using sort of a Python pane of glass in front of the data that just lives in the database. When it comes to predictions, same thing, but also having sort of a more reliable, a quantitatively more reliable predictive model when you incorporate these spatial effects. And so the statistics that you can get to evaluate the performance of a model, you can actually see when the model is generating more reliable results based on test and validation. So I think I'm right at the top of the hour, and I don't know if there were any questions or anything else, Denise, but if not, I think we are probably done. Denise, were there any questions or anything else here to?
There were no outstanding questions.
So
Thank
do you
you to
want
Hans for
to?
answering them.
Yeah, so I'll stop sharing if you want to share, like if there was like a closing slide that you had on the link for the Ask Tom sessions, maybe as a closing thing there.
Great. So let me share my screen. Okay. Can you see my screen?
Not yet.
Oh, sorry. Okay.
There it is.
All right. So thank you, as always, David, for your very interesting conversation. And here are all the resources on Oracle Spatial. I'm putting in those links there. And just quickly, our July Ask Tom session is going to be really interesting. We have some special guests from ITIS Corporation to discuss the development of custom maps with Spatial Studio, Apex, ORDS, and GeoJSON. So we would love to have you join us there. Thank you all for coming, and we'll have the recording up on the session in just a couple of days.
Thanks, everyone. Thanks for your attendance.